we will use IMAT today to set up a flat 3D model from scratch to the point of at least running. And then we can have a look at the solved model and we can post-process the data, create movies, and so forth. I've just started IMAT again, and my license is active, and you can see that in my recent projects, I've got this Mine A project that we work with. So I'm going to load that project, and you'll see that we start off today exactly where we left, where we closed yesterday, basically. So IMAT saves the project as you go. So there's no need to constantly save your project. It basically remembers every single change that you make. So if I were to, for example, turn block models on or off, or turn seismic data on or off for models or some geometries, it will remember that each time you make that change. So there's no need to save the project constantly while you work with it. So let me just get set up here. So I think we left off yesterday by looking at seismic data. This was the data we were looking at. So I'm going to turn my seismic data off with this eyeball button that I explained yesterday. And I'm also going to hide this geometry. Now, one thing that I did not show yesterday is the legend. So the legend is similar to the other iTasker software, although it can be interactive as well. If you want to hide an item, for example, you can simply select any one of these items, click on it, and it will hide it from the 3D viewer. If I want to, so currently we're looking at contours on these excavations, and you can see the color legend here. I can simply hide it, or sometimes you do want to keep the legend in for a snapshot, for a report, for example. If this entire legend becomes too convoluted and you just want to hide the color legend, you can right-click instead of left-click, and it will appear in the hidden legend items in the information window and will be removed here from the 3D viewer. But its contents will still stay visible. So left-click is hide an item from the legend here, and it moves it into the legend, hidden legend items view here. You can then right click again to bring it back, and if you left click, it completely hides the item. Another way to quickly hide items from the 3D viewer is to hold in shift and click and select the hide option. Or if you want to find where it is in the project, obviously, this is some geometry that's visible, and I need to go and find the specific item that I want to hide. It might be difficult at some point. You can shift and click, and you can find it in the tree, and it will highlight that item in the tree for you. So let me just turn my geometries back on. I'll turn my undercut and extraction levels on. And before I start building my flat 3D project, I've received new data from a client, for example, or surveys provide new mine plans. The mine's got a new stress state. We're going to look at all this data first, and then we're going to jump into building our flat 3D model. So the first thing we usually get for a mine is the in-situ stress state. So I've got a picture here of the specific mine stress state. This is not specific to this particular mine that I'm using here. I've actually modified it. So the stress state here doesn't apply to any mine. It's a modified version of the stress state. So I'm going to go ahead, and yesterday I showed in the project settings, we want to define our in-situ stress, our project-wide in-situ stress here. So if you bear with me, I'm just going to jump ahead, and I'm going to set the in-situ stress. I'm just moving the picture over. So apologies for that. I'm just moving this over to another screen so I can type. So my datum, or my free surface level, was at 1300. I want to add gravity to my model. The stress field has got a 10 MPa fixed component. And note, when you look at the the in the properties window, the description of that stress field, it tells us that IMAT works in a compressive positive stress field, stress state for mines. This is simply to reduce confusion for our clients. We know scientifically that the stress state needs to be entered in a compressive negative way. When IMAT interacts with flat 3D, these conversions happens automatically in the back end. But in IMAT, we are required to enter the stress field in a compressive positive manner. So, for example, if I were to enter a negative value here, IMAT warns us, you have entered a negative value, a compressive positive convention is used, you want to continue. So you can override this, you can jump ahead and put that compressive or a negative value for stress in there, but keep in mind IMAT uses a compressive positive convention for stress. So I'll just continue typing in all these fields for the stress state. Sigma 1's azimuth is 60 degrees. Sigma 1 plunges 0 degrees. Sigma 3 is 150 degrees. You'll note that we do not have to enter the direction for Sigma 2. That's because we can automatically calculate it because the principal stresses should be orthogonal. So this is just an additional step to ensure that we keep it as simple as possible for the user. The principal stresses are required to be orthogonal, so therefore we can calculate the direction of Sigma 2. And also, a few times in the past, I've received stress states from the mine, and the actual stress field is not orthogonal. So that in itself is a problem on its own. So this process in IMAT fixes that automatically. Also, if Sigma 1 were to not plunge at 0 degrees, let's say it plunged at 10 degrees, then we don't need to enter the Sigma 3 plunge as well, because we can then, based on the orthogonality rule, we can calculate the plunge of Sigma 3. There's just this one edge case where Sigma 1, when it's 0, that we do need to enter the Sigma 3 plunge. So that's just one exception to the rule. But by default, you should only have to enter 3 directions if Sigma 1 plunge is not 0. So I've just set the project-wide in-situ stress state. The next thing that we usually get from the mine is a set of material properties. The material properties for the different domains that we do want to use in the model. So we either get those in a tabular form or a spreadsheet, or they can provide the information in terms of a block model. So I've got a simple block model loaded for this mine, and these files can become very large. I've just got a simple block model of an X, Y, Z coordinate. This model's for each coordinate, we've got a Young's modulus, Poisson ratio, density, and then some columns or some of these values have got UCS, GSI, and MI, but as you can see, they're not available everywhere. So I'll just scroll down. You can see in some instances these fields are populated, and in other fields they're not populated. So what we're going to do is we are going to import this block model data using IMAT's CSV importer, and we're going to have a look at this block model, and then finally, when we build our flat 3D model, we're going to use this block model data in the flat 3D model. So what I've done, usually just for myself, just to make things easier to see in which columns the data is located, I've inserted a new row, and I've just marked the row numbers for myself just to easily see what the columns numbers are that I do want to import. So I'm just going to again move this to my other screen, and I'm going to go ahead and import this block model data. So I'm just moving that over quickly. So for this, I'm going to use the block models plugin. And to import a block model, you'll right click, import block model, and select that CSV file. And similar to what I showed yesterday, the generic importer, you need to specify in which columns what information, where to find the information. So I'll call this the mine model. Mine model 1. You can import as many block models as you like. For this particular mine, the block model, the original file that we got from the mine was 50 gigabytes, which is insanely large. So we split it into several smaller files to make it smaller, and we can then import those smaller files individually. So yeah, I'll give it a name, mine model 1. So the block model file does not have, the coordinates in the block model file does not have to come from a regular grid. It can be a file where, for example, we've got lots of information in one area of the mine and less information in the other. So it doesn't have to be a regular grid. But when IMAT imports it, it regularizes it. So it basically calculates the upper and lower bounds of the block model on the file. We create a regular grid with a certain cell size. So I'm going to use a 25 by 25 by 25 cell size, and it regularizes that information. Next, we need to specify in which columns the X, Y, and Z coordinates are located, and that's located in columns 1, 2, and 3. These are compulsory. So if your block model does not have X, Y, Z coordinates, columns for those coordinates, then you cannot import the block model. Then we have some optional fields, and based on the constitutive model that you want to use in your flat 3D model, you will select which columns to import. Again, you do not have to import everything. You only pick and choose the ones that you do want to import. So my particular block model has got Young's modulus, and that's located in column 4. It's got Poisson's ratio, that's located in column 5. Then I've got a density, that's located in column 6. I've got UCS, GSI, and MI in column 7, 8, and 9. Now here, I just want to point out quickly that you'll see, for example, for depending on the constitutive model that we use, there's a UCS for IMAS, GSI for IMAS, and a MI for IMAS. Also, there's an intact Young's modulus for IMAS. The reason why there is for example, a separate Young's modulus and an intact Young's modulus in IMAT, or maybe even a UCS for IMAT and let's say an MI for Hooke-Brown, is because when IMAT interacts with flat 2D, it needs to know which properties to set on the zones. So you need to be specific, or you need to know beforehand which constitutive model you're going to use. So here's a good example, like GSI for Hooke-Brown or GSI for IMAS. So for this example, I am going to use Hooke-Brown, or actually no, I can just go ahead and use IMAS. So I'll import a UCS for IMAS located in column 7, GSI for IMAS located in column 8, and an MI for IMAS located in column 9. And I also want to import the intact Young's modulus instead of the normal Young's modulus that was located in column 4. So I'll go ahead and import that information. Shouldn't take too long. Great, so it's just imported. So this, before we get to the point of building a flat 3D model, we first want to inspect the block model. And there's a few ways that we can inspect the block model. If we simply turn our block model on, this shows the grid. This shows the extent of the block model that I've imported. So these are the bounds with the different material properties. When I expand it, you can see all the different properties, material properties that I've imported. So, for example, I've got the intact Young's modulus, GSI, MI, etc. Now, let's say, for example, I want to visualize MI and how it changes in this block model. So I can turn MI on, and we get, similar to normal flat 3D, we get a cut plane that we can use to move through this grid. And to modify the cut plane, you can simply use the mouse wheel to move through that, and you can see the legend here for the different value for this cut plane as we move through it. You can move the cut plane like in different orientations and simply again roll your mouse wheel. So a cut plane is the one way that we can use to visualize block model properties. Another way we can use to visualize it as isosurfaces. So if I select my property, default is cut plane, and the data mode can be isosurfaces as well. So again, it adheres to this color legend here, and we can see the isosurfaces for the cut plane, and we can specify how many isosurface levels we want, for example, etc. Probably the most useful way to look at block model properties is to interpolate it onto some wireframe. For example, if you had a pit of the mine, or in this example, I've got a cave, you can interpolate those properties onto the actual wireframes of the model that you do want to use. So the third way to visualize it is using the wireframe option. So I'm going to interpolate MI on my cave shape 21, and here you can see what that looks like. You can interpolate it onto multiple geometries, so I can interpolate it onto my excavations as well, or maybe a free surface, or even some structure, for example. So those are the three ways that you can visualize block model data. Again, we still haven't used it in the flat 3D model. It's purely visualization at this point. So I've imported my block model, and I'm finally ready to start building my flat 3D model. And to do that, we will use the Flat 3D Advanced plugin. Now, just a brief introduction between the difference between the Flat 3D Advanced and the Flat 3D Basic plugins. The Flat 3D Basic plugin is a simpler version of the Advanced plugin. With the Advanced plugin, you can build extremely complex models. You can have, for example, hundreds of different domains with different material properties, thousands of mining steps. The basic version is meant to simplify that. And typically it's for those users that only have one material or an elastic material, typically an elastic material or a hook ground material with only a few mining steps. So a good example is for those existing Map 3D users that uses the boundary element method with a single material. If you have an existing Map 3D project of your mine, you can simply right-click import the Map 3D project, and this will set from the Map 3D input file will set up the entire Flat 3D project for you with all the material properties and stress states and geometries from the input file. I don't have an example of a Map 3D input file for this particular mine, so I'm going to go straight ahead and jump into the Flat 3D Advanced plugin. So I'm going to create a new Flat 3D project, and I'll call this maybe project 1. And then I need to specify what types of geometries am I going to model. Does my mine have caves? Does it have drawbells, pit shells, wing stopes, etc.? You can only choose one. For example, if you want to use it only one, or tunnels, that's fine. But when we build the model later on, you'll see the order in which the model is built. For example, tunnels have preferences above caves, so you typically do want to specify or import the geometries separately. So for this mine, I've got tunnels, I've got caves, I've got rings, and I've got drawbells. I do not have a pit shell and I do not have stopes. And it's created this project Flactally or project 1. Note that you can have an infinite amount of Flactally projects if you like, not limited to one. A good example is if we want to calibrate a numerical model, we want to test different material properties or test different stress states. Each project can represent something, a different instance of that calibration. So I'll just give you another example. I'll create, for example, maybe I'll call this calibration 2. And again, I'll just select thermals in this simple example, and there's my calibration 2 project. So you can have as many as you like. Now, let's say for argument's sake, you did have 10 separate Flactally projects here, each representing different material properties. If you don't name the project properly, it can become confusing what properties you use at what point. So there's a field on each project called the project notes field. So let's say, for argument's sake, this will just be my first model where I'm going to test all the default properties that we receive from the mine. And then maybe for calibration 2, we're going to modify, let's say, Young's modulus. So I can add a note to my project set. And just for myself in future to know what I actually modeled in this particular project. So I'll call this, say, in this project, I used all the default properties. Then, when you have a look at the information window, in the project note, there will be a section for project notes, and it will, the notes that you typed or will be written here, and it will also, of course, still be available in the properties window, but in the information window, it's just a bit more clear. Also, note while I'm here, I actually see that I've added a few how-to videos. There's one video here, how to build a basic model. So you can click on this, and this will go to the YouTube channel. And most of the stuff that I'm showing you today is going to, it will be shown in this YouTube video over here. There's also a second how-to video, is how to extract seismic events from a numerical model that's got plasticity. So if you do want to go check that out, simply click on this video. All right. So I've got project 1, and just for myself, I'll say for calibration 2 project, I'll say I've modified Young's modulus %. So at least I've got some idea of what I'm doing there. All right, so I'm going to build my project, or go through the process of building my first Flactally project. And the project layout, or the layout of the items in this tree under the project, is typically the workflow that we follow when we build numerical models. The first thing we have to do is set the in-situ stress of the project. So I'll click on that, and you'll note that this field is already pre-populated with the values that I've set on my global in-situ stress for my project. So I've set it once previously. When I create a Flactally project, it's already set for me, so I don't have to go and type it in again. Of course, now I can go and modify this. I can modify any of these fields if I want, especially for a calibration. If I want to test a different stress state, you can modify it, but at least it saved you quite a lot of time by typing in all these values yourself. So in-situ stress, check, that's already done. I don't have to do anything there. The next thing we have to do is specify the boundary conditions of our domain. By default, most of the time we use fixed boundary conditions on our domain, but you are also free to choose roller boundary conditions or traction boundary conditions. Ideally, if you have maybe a free surface or open pit, you can have a free boundary and the upper Z. For this particular mine, I'm not going to model all the way up to the surface, so I will have a fixed surface boundary at the top. So I've just set the boundary conditions. I can move on to the next step. Next, I need to specify the mining sequence. And the mining sequence will be used to when we apply something called grouping logic, when we mark certain zones to be mined out at certain stages. Now, for this particular project, let me just have a look at how many mining steps I have. So I've got in my Geometries folder, I've got caves, drawbells, rings, tunnels. So I've got tunnels, and I've got step 1 assigned to it, and I've got 21 steps of caves for this model. So I'll jump ahead, and I'm going to create 21 mining steps. And to do that, on my mining sequence, I will create new steps. As I mentioned, I have 21 mining steps. I'm going to start at step 1, and I've got a total of 21 steps. I need to specify the start date of my first step and then the interval that each step represents. Now, I know my seismic data starts in January 2010. So if I want to compare modeled seismic data, for example, with real seismic data, I need my times to match. So again, this concept of time that I mentioned yesterday, that's extremely important. So I'm going to start on the 1st of January with step 1, and then have 21 monthly steps. So it's just created those for me. So there's step 1 to step 21. You'll also note that there's an equilibrium step and an initial step. I will explain a bit later on what those steps mean. But for now, I'm just going to import the geometries. Also, you'll note that the text of these steps are highlighted in red, or they're written in red. That means that I haven't solved this particular mining step yet. When it's solved, this text will become black. So this is just a visual indicator to see that whether the model has been solved or not. So a good example is, let's say I start solving this particular model overnight. Something went wrong in step 8. I can at least see I got all the way to step 8, and I can fix the problem and continue from step 9. So this is a visual indicator of whether a model is solved or not. If I expand, for example, for step 1, this is where I can see my tunnels, rings, and drawbells. Those fields that I specified when I created my project first. So I specified that this project has got tunnels, it's got rings, drawbells, and caves. So it is here where we need to import our geometries, whether it's DXF files, STL files, or some other format, maybe circuit file formats where we need to import it. Now, one option is to import each and every geometry one by one. But as you know, that can be extremely time consuming. So what I've done is I've named my files in such a way where I've got, for example, cave_1. This means this is a cave belonging to step 1 and step 2 and step 3. If you name your files in a similar way, where IMAT can interpret the step number from the file name, you can automatically import it. Now, you do not have to, for example, have this specific format. You can have, for example, 4_cave as well, or you can have cave4 or any format like that. So IMAT parses the file name, tries to find the first number in the file name, and tries to build then the largest number in that sequence. So if you, for example, had even the date assigned to your file name, let's say 2010-0101 _cave_4, this would not work because IMAT would find this number and it would look for a step with this sequence. But if I had a file name something like this, let's do that, 4 underscore cave underscore 2021. This will work because IMAT finds the first number and it tries to pass the largest number after the first number until it can't find any numbers anymore. So it will basically break in the underscore. So this is a typical naming convention that you can have for the files for IMAT to automatically import it for you. So there's two ways to import it. You can right click on your mining sequence, import, auto assign geometries. I'll just browse to my cave, for example, and you can select all those files and then specify it belongs in the caves folder, and you can automatically import the caves. There's an even easier way. So I've gone ahead and I've named my folder caves and drawbells and rings and tunnels. These folder names that's got all my geometries in match the names of these folders. So all I have to do is I can use the option auto assign geometries from folders, not this one that I showed previously, but from folders, where then you simply select the folders that you want to import and say open, and IMAT will import all of that for you. So it will tell you, so it's parsing, for example, this file name. It found step 8 and it imported it successfully. So let's see if rings underscore 8 is in the rings folder of step 8. And yes, there it is. So I've just automatically imported all my geometry, and there was probably close to about 200 or 300 files here that I've just imported. Now, what I can do is simply click on the eyeball and have a look at my mining sequence. See how that makes, what that looks like. So obviously the caves are convoluted, but that all looks fine to me. Again, I can quickly hide it if I want, but I've just imported my mining geometries. And I'm ready to continue to the next step, specify my model domain. Actually, I'm going to just turn my mining geometries back on, because now I'm going to have to specify the domain that I'm going to use for this particular model. So next, I will turn on my domain. And this is typically that command that we use when we select the bounds that for our numerical model, that zone, create, brick, and specify the bounds. So instead of creating a brick, we're going to create a box, a spatial box like I showed yesterday, and I'm going to create this model domain. Again, we can use the controls option to translate this box and move it. But I want my box, for example, to be centered around that point. So in the properties window, I can type in my center coordinates manually, or I can select that button and then click a point in the 3D viewer, and the box will be centered around that position. Now, we know that usually a good rule of thumb is to have our boundaries of our domain about 5 to 10 times away from or the extent of our excavation. So I'm going to just manually type in some values and eyeball a rough guess for the extent of this domain. Maybe I'll just move it up slightly, translate it in the Z direction. All right, so this domain might still be a little bit small, but for the purposes of this presentation, I'm going to assume that this domain is fine. Now, we are going to build an Octree style model of this domain. So we're going to start with we're going to discretize this domain with a certain cell size, that's this global cell size, and then we're going to specify refinements near our excavations or near the cave. So we want to start with a core cell size and refine our way down. So I'm going to, let's say, use a global cell size of 20 meters and add certain refinements closer to my excavations. So I've got my domain. I'll expand my domain, and there's an option for refinements. So again, I'm going to use a 20 meter core cell size or large cell size, and I'm going to refine, let's say, for example, down to 2.5 or 2 meters close to the excavation. So I'll add my first refinement, call this my level 1 refinement. And it's quite powerful in terms of what you can do or how to actually specify these refinements. And each one of these items are called refinement rules. The first rule, for example, above elevation, allows you to specify some elevation or Z level and refine all zones above that elevation to a cell size of your choice or a zone size of your choice. The one that we're going to use here is the distance from geometry, and that's probably the one that most of us use when we write our in flat 3Ds. We specify some distance from the geometry that we want to refine. This allows you to select the geometry wireframes and do those refinements. This one, a mining step, is a very powerful refinement as well. You can select a mining step number in the mining sequence, and it will basically use all geometries. Let's say, for argument's sake, I'll just quickly demo this. I will have my level 1 refinement, and I can say, I want all geometries maybe within 40 meters from mining step 21 to be refined. So this will use all the geometries that I've imported, and it will use that basically at everything, or every zone that locates within 21 meters of those geometries will be refined to one level, down to 10 meters. The reason why I'm not going to use it for this particular example is I don't want zones to be refined near my cave. I only want it to be refined near my tunnels. So because I've imported cave shapes as well, I cannot, or I choose not to use the mining step refinement. So I'll just delete that quickly, and I will add again my level 1 refinement. And this is the one that I do want to use. Just before I select that, I quickly want to describe some of the other rules. So there's also a polyhedron geometry. So if you have a wireframe, a closed surface, for example, of a lithology, you can select that and it will use that arbitrary shaped wireframe. All the zones that are contained within that closed volume will be refined, or you can select a rectangle, a point, and a rectangle refinement. Or if you've created a spatial, the spatials that I showed yesterday, for example, a cylinder or an ellipsoid or an arbitrary polygon, you can select a spatial using this rule. Or if you want to click a point and a certain distance from that point you want refined, typically maybe if you've got a crusher chamber close to a crusher, you're modeling a crusher chamber and you want to refine that, you can click a point and a distance from that point will be refined. But for this particular example, I will use the distance from geometry refinement for level 1. So I'm going to add one level of refinement. Let's say 80 meters from my excavation, from my tunnels. I'm going to refine down to 10 meters, and I obviously need to select the geometries in my geometry plugin. So in my tunnels, yesterday I created this combined development. So all zones within 80 meters will be refined down to one level. I'll do exactly the same for level 2. I'm going to use a distance from geometry rule again, but this time I want 2 levels of refinement, maybe all zones within 40 meters from the same geometry. You can also do it simply in one step. I could have said level 1, I want 3 levels of refinement from 80 meters or 20 meters from my tunnels. You could do it in one step as well. That will work fine. But just for demonstration purposes, I'm going to manually add 3 levels of refinement to this into my model. 3 and maybe 10 meters from my excavations, I'm going to refine down to 2.5 meter levels. So Same story. Done. So just to reiterate what I've done, I've created a domain with 20 meter cell size. I have all zones within 80 meters of my tunnels will have one level of refinement down to 10 meters. All zones within 40 meters of my tunnels will have 2 levels of refinement down to 5 meters. And then finally, all zones within 10 meters from my tunnels will have an additional refinement of 3 levels down to 2.5 meters. So I'm nearly done. I've just specified my Octree grid and what I want it to look like. The final step is to set our material properties, our material domains. And this is typically where we can specify certain block model properties, and I'll show you how to do that in a second. When I expand the material domains, you'll notice that there's a host rock. So by default, we need to initialize all zones with a certain material. Then we can add as many subdomains as we like. Now, I've got 3 different subdomains that I'm going to use in this example. So let me see if I've already imported them. Yes, I've already imported these lithologies. So that's what they look like. So let me just quickly randomize the colors again just to see. These are the 3 subdomains with different material properties that I'm going to use in my model. So I'm going to add a new material domain. The quicker way would be to just simply select those geometries and add them. So let me quickly show you this. And then I'll take you through the more manual process. So just selecting those, and I'll specify these are polyhedron, so they're closed volumes geometries. And now all the 3 subdomains are manually created or automatically created for me. All that's left for me to do is to actually specify the properties. I'll delete this and I'll go manually through the process of creating these domains. So I'm going to create a new subdomain, call it domain 1. And again, similar to how I've specified the refinements, there's similar rules on how we can actually specify subdomains in this model. The first thing, or the first rule here, domain boundary layer. This one is, it's an interesting one actually. What this one does is it basically takes all zones within a single layer from this domain, this boundary domain that I've created here, this box here, a single layer of zones, and you can specify that to have a certain material property. And the reason why I added this is I found that if you make the domain boundary, a single layer of zones on the domain boundary elastic, you get the model to reach equilibrium quicker, especially, well, if you've got a plastic model. That helps with all these zones that typically fail on the corners and the boundaries of our domain. So this allows you to quickly and easily just specify an elastic layer around the boundaries, and this allows the model to solve quicker. The next one allows you to specify an elevation and specify material properties in that way. For example, if you've got a free surface at a specific elevation, you can null all zones. We can basically define null zones above a certain elevation. Alternatively, if you've got a layered media, like a coal mine, for example, you can have multiple layers or multiple elevations and specify different material properties for each one of those layers. Again, there's also a distance from geometry. So let's say for you had structures with thickness and you want to create ubiquitous joints for those structures, you can say, I want maybe all zones within 10 or 20 meters from my structures to have maybe IMAT with ubiquitous joint properties. There's a default rule. Basically, it overrides all zones with a certain property. Then there's a plane 3D. You can specify a plane with an arbitrary orientation, and all zones on the positive side of the plane can be have certain material properties. The ones that we're going to use here is the polyhedron rule. So we've got a closed surface for each domain, and we want all zones inside these separate domains to have certain material properties. There's also a geometry raycast, and this is the one that we typically use in Flat 3D. It uses a raycasting algorithm to try and find out whether zones are inside or outside the polyhedron. My experience is that the one in IMAT, the polyhedron geometry one, is a lot faster. You can go and use the raycast one if you want, but these two do the same thing. I just find this one to be more accurate, faster, and this one tends to not work when you've got overlapping or overlapping facets in your geometries. Also, you can have a spatial volume, a box or a cylinder where you can specify certain material properties, or above surface topography. So if you had a free surface and you've actually got a pit shell maybe in there, or a mountain range, you can select this rule, and then it will allow you to select the wireframe of that free surface, and you can, for example, go and null all zones above that free surface. So I'm going to use this one, polyhedron, for my domain 1, and I will do exactly the same for domain 2 and 3. They are polyhedron geometries. They're closed volumes. Domain 3, they're polyhedron, yes. All right. So you'll notice that each one of these rules that I have created, it's got a number next to it. And this is extremely important because the way that it's implemented in IMAT actually allows you to build extremely complex geometry. So for example, you can see that this blue domain here, this blue lithology here, it overlaps with this gray one over here. So domain 1, I'm going to link to the domain 1 in my lithology here, and the same to my domain 2 in my lithology. And then finally, domain 3, point that there. So what will happen is once IMAT has built the Octree grid, it runs through all zones and mark them first of all as a host rock material. Then it runs through all zones again, and those that adhere to this rule, and it's more specifically those zones that fall within domain 1, this gray zone, they will be marked to have this material properties. Then it will run through all zones again, and if it falls within domain 2, you can see there's overlap here, they will be marked as domain 2. Now, typically, if I just add some transparency to domain 1, you can see that there's overlap there. So all the zones that were initially marked as domain 1 in this overlapping region there will now be marked as domain 2. And then the same for domain 3. You can see there's quite a bit of overlap between that. So all the zones that were initially marked as domain 1 and maybe even potentially domain 2 will now be marked as domain 3. This makes it quite powerful because if I, for example, want to add maybe another structure intersecting this, I can go and add another material domain rule, maybe call this my structures rule. Use a distance from geometry rule, link to my plane. So I'll select my plane geometry that I've created previously. And let's say, let me just see where this plane is located. So the plane is located in there. So if I use this distance from geometry, I can say, well, all zones that locate within 20 meters from my structure need to now be assigned as a structure zone. So these zones, especially that was close to the structure, they were first marked as domain 1, then marked as domain 2, and then potentially marked as domain 3. And finally, those properties get overwritten as structures. So I hope you can see that this makes it extremely powerful in terms of what you can model. Finally, if you were to, for example, have a free surface wireframe that I do not have here, and the free surface somehow cuts through here, you can specify the free surface as your final domain and go and null all zones above the free surface. All right, so I've just specified all my domains and all my material properties. I've specified mining sequences, and I'm finally ready to build the model. So to do that, you right-click on the grid and you build the grid. You'll notice that similar to my mining sequence, this was highlighted in red, which previously showed the model's not solved. The grid is currently red, showing that I haven't built a grid before. And it's quite simple to build a grid. You'll right-click, build grid, and there's 3 steps involved in building the grid. Basically the same 3 steps that we've just followed, but first of all specifying a mining sequence, then specifying our domain and our refinements, and then finally our material properties. So there's same 3 steps we can do with a grid. We can just simply choose to do all of them simultaneously, or we can do one at a time. So for example, we can only build the Octree grid first to see how many zones we are going to end up before we apply material properties or the mining sequence logic. For this example, I'm just going to go ahead and just for the sake of time, I'm not going to build all 21 mining steps. I will just build 10 steps and then visualize it and then see what we have. So I'll say OK. And this process will probably, from memory, take about 5 minutes or so. So it just finished the first step, and it tells me my grid has 1.2 million zones and 1.3 million grid points. Do I want to continue? I'll say yes. It actually feels not a lot. We'll see. You'll notice that I actually haven't set the actual properties. I'm just building the grid. We can modify the properties later on. So currently everything is still marked as elastic, but I'm going to override that later on after I've built my grid, just to see what that looks like. Actually, while this is busy, I can do that now. So I'm going to mark all my domains as IMATs. So I'm going to use the IMAT material for all these domains. And you'll notice, so for example, if I were to change elastic, then I only set Young's modulus, Poisson ratio, and density, for example. If I change to IMAS, then all the IMAS properties becomes available for me to set. It is here where it's actually also important. It's finished quite quickly. We'll have a look at that in a second. Here is where we can override the material properties with the block model that we've imported earlier on. So if I, for example, want to override the domain 1 material properties with the block model that I've imported, there's this option, use block model, and you can select the block model that I've imported. Then those properties that applies to the IMAS material that I have imported, you can choose to override it. So what IMAT will do is it will go and find those zones in domain 1, and it will find the closest point in the block model, and it will write out a separate file, a CSV file, with zone IDs pointing to the block model properties that I want to override. And when we get to the point where we want the IMAT solves the flat-free model, or basically generates the data file, it will make a bit more sense on how to do it. So the logic works. We need to specify for each domain default properties. I'm not going to worry about the default properties now, but you for each one of these domains, you specify default properties, and then you can go and override those properties with block model properties if you choose to do so. All right, so let's have a look at our grid. Let's see what the grid looks like, and maybe we might have to rebuild it, and do some further refinements. All right. So I'm going to hide my caves. And I'm going to hide my current mining sequence, and I'll just turn my development on and see what my grid looks like. The first thing that we want to look at is our refinements. Did the refinements actually do what I wanted to do? Yes, so in the refinement slot under the 2.5 meters group in the flag 3D grid, these are all zones that was refined down to 2.5 meters. The default way that we visualize them is with points. You can go and turn that into faces as well. It just takes a little bit longer time to build it, but this is the outline of all the zones that are refined down to 2.5 meters. The same for zones 5 meters, and then 10 meters, and finally everything will be 20 meters. So let me just show these as faces as well, so you can see. So there's my 10 meter boundary, there's my 5 meter boundary, my 2.5 meter boundary. So the refinements work exactly as I wanted to. I'm happy with my grid in terms of refinements. I've got the refinements correct. Next, I want to see if my material domains were constructed correctly. So remember, previously we had 4 domains. I want to see if those material domains were constructed correctly. So there's all the zones. Domain 1, again, it's rendered as points. I'll just turn them into faces. There's the outlines. And if I turn domain 1 on, you'll see only those zones, those few zones, have got remaining material properties marked as domain 1. This is important. Remember, I mentioned that the logical or the order in which I specify this is important. So obviously, domain 2 overrode that part, those zones there. So they should theoretically be part of domain 2. So let's have a look. Let's show them as faces as well. Oh, there we go. And I'll change the color just for better visualization. There's domain 2. And then finally, domain 3. Again, let's just read it as faces. There's domain 3. So, is it captured inside there? Yes. You'll notice that it's cut off there. That's obviously because it is outside my model. So that is my domain 1, 2, and 3 marked correctly. Right. Finally, I specified structures, zones to be structures, and I actually want to set those as ubiquitous joints. So I'll mark those as faces as well. So, yep, I'm happy with domain 1, the domains that were set in the flag 3D grid. Finally, I want to have a look at my mining sequence. I want to see if my mining sequence was correctly assigned. So you'll notice that there's names here: tunnels, rings, caves, drawbells. Those agree with these attributes that I set to my model initially when I created it. So first, under tunnels, step 1, these are my step 1 tunnels. Again, let me just render them as faces. There we go. So there's my tunnels, and it looks not too bad. All right, so if I expand my rings, there were only rings in steps 2, 3, 4 to 10. Remember, we only built 10 steps, so I'll visualize those as faces as well, and I'll turn it on. So there's my 10 mining steps for my rings. That looks good. Drawbells, I've got a few drawbells. I'll turn those on as well, render them as faces, and they should be down there. Yep, that looks fine. And finally, my caves. I've got caves for 10 mining steps. Turn them on, also render them as faces. There's my caves. So I'm actually pretty happy with how this model turned out. And I'm at the point where I can start solving the model. I will probably just quickly review my material properties to make sure that my material properties are, I'm happy with those. GSIs, MI, all of those, I think that's fine. I'm only for this example going to override domain 1 with these block model properties. For structures, maybe I can choose to use a strain softening model instead of IMAT. I can include joints if I want. What this will do is IMAT will you can set, well, first of all, you can set the ubiquitous joint set properties for those zones. It will find those zones with a structure, and IMAT will automatically set the zone normals or the normal properties for those ubiquitous joint sets. And I'll show you in the flat 3D when we get to the data file what that looks like. So I'm including my joints, and I can specify the joint set properties. And again, I can override material properties if I like. I can, I mean, block model with different block model properties if I like. So yeah, go create quite a powerful model. Okay, so I'm finally ready to start solving my model. For the average user, the user that's not used to fish, you can simply go ahead, right-click, and solve project. I'm not going to do this. This will start up a flat 3D console version, and it will start solving it. Build solve data file. Call this my solve1 data file. And this should look familiar to all of you out there that are existing flat 3D users. So based on all the settings that I've specified, material properties, domain settings, in-situ stress settings, IMAT automatically creates the data file for you to run through the entire mining sequence. So this looks familiar, model new. It creates certain fish functions, functions to save stresses, displacements, plastic strains. There's a fish function to load the model state. So let's say, for argument's sake, I've got 10 steps in this model, and I've solved everything through to step 5, and I want to continue from step 6. There's a function that can load the previous step data and continue automatically for you. Here's a function that loads the flat 3D grid file, so you'll see it points to the correct location inside the IMAT project. It loads the grid file. Here's the function that set all those material properties for you. So zone, C model, assign, IMAT, range group, default slot domains, sets all those properties based on what I've defined here. And let's say, for example, domain 1, got Young's modulus 70, density 2700. So there's exact 70, density, etc. There's structures. What I might do quickly is I'll rebuild the grid, because I actually modified these properties to include the block model later on. So just bear with me for 1 second. I want to show you how we can change that as well. So I'll rebuild my grid. Grid already exists. Do you want to overwrite it? I'm not going to reconstruct the Octree grid. I'm not going to reapply mining sequence logic. I just want to reapply my material domains. So we'll just quickly go through that. Shouldn't take too long. And this particular function will be extended. So I'll build a new solve data file, call it maybe solve2. Now if I look at this particular function, material properties, so now it's got some extra functions in there. So remember, I overrode domain 1 with a certain block model properties. Now there's a CSV file with certain zone IDs that needs to get overridden. It loads it, loops through all of it, finds the zones, and overrides the properties with the block model properties. Also, remember, I added structures with ubiquitous joint sets. There's extra code. First of all, there's data vector import joints. So it imports all those zones that are ubiquitous joint sets, and IMAT is clever enough to know whether you're using SUBI ubiquitous joints or IMAT ubiquitous joints, and it sets those properties automatically for you, those joint normal properties. If let's say, for example, I want to go and overwrite domain 1's density, then all I have to go and do is change, maybe say density from 2,700 cubic meters, a kilogram per cubic meters to 2,800. Rebuild my data file. We call it solve3. Now, if I go down here and look at that, density 2,800. So you can modify properties on the fly and rebuild your data file to go and solve it. Here's the function that applies the boundary conditions. Remember, we specified fixed boundary conditions everywhere. So here's your zone, grid point, fixed velocity, range group, position, blah, blah, blah. This should all look familiar to all of you. Here's a function that sets the in-situ stress based on what I've defined in the in-situ stress function over here. So this sets the in-situ stress on all the zones here. Again, so if I want to, for example, change the datum or any one of these properties, I'll just change the datum and rebuild my data file. Solve4, go back down to the in-situ stress. You'll see there's my datum is changed. So again, you can change properties on the fly and rebuild these data files. Then there's a function to extract, if you've got a cave in your model, to extract that cave and set the cave properties, the cave bulk modulus and shear modulus for each mining step. There's a function to extract each mining step. So you should all recognize this: zone relax, excavate, range group, mining step, slot rings, tunnels, etc. So this should look familiar to you. And then there's the master function that basically loops through all the mining steps from step 1 to step 10. Save stresses, plastic strain, displacements for each one of those. And yeah, basically loops through the entire mining sequence. Now, one thing that I've actually neglected to mention is that IMAT doesn't use save files at all. Save files, FLAC3D save files, as most of you know, become exponentially or grows exponentially with the size of the model. So typically, what we want for IMAT is almost like the equivalent of a save file for each mining step. So if you can imagine, if, for example, for this particular model, we've got 100 mining steps with 100 save files, those, first of all, become very time-consuming to load, and it uses an enormous amount of data on disk. So IMAT doesn't use save files. Once every mining step is solved, the models reach equilibrium for that mining step. The zone stresses are saved. It's a file called stress.bin. So this file contains a zone ID with a stress tensor. The plastic strains tensor for each zone is saved. So similar to the stress, a zone ID with a plastic strain tensor. And the grid point displacement. So displacements.bin file. So it's a file containing grid point ID with the displacement vector is saved. And this is significantly smaller than the save file. And this is all that these three files, with these three files, we can basically continue runs or restore existing or previous model states. So these three files together with the existing FLAC3D grid file, we can continue runs, and we've got all the information we need to do post-processing. So yeah, no save files in IMAT. And then finally, this is basically where outside of all the fish functions, so this is where it starts, model configure plugin. We've got a few separate plugins. This will fall away in future versions of FLAC3D. We've got special versions, libraries or plugins of the hook model, the more cooler model, Subi and IMAS, to save the full plastic strain tensors for each zone. This is especially important if we want to, for example, extract seismic data from a numerical model once it's solved. These plugins are used to save the full strain tensor. This should look be familiar to all of you. If the IMAS model was chosen in any of the domains, model configure IMAS, it sets the program directory to the Flag3D project inside IMAT. Then we start the sequence. We load the grid, set material properties, set the in-situ stresses, apply boundary conditions, run an initial equilibrium solve, and that is where this part comes in. So we've set the in-situ stresses, but usually we run our solve sequence just before excavating anything, just to get that initial equilibrium step. That refers to this step. The stress and displacements of all zones for the equilibrium step is saved here. And then that's where we save stress after it's reached equilibrium. Zone initialized, grid point displacement 0, 0 should look familiar, and then run through the mining sequence. Now you'll notice for each one of these solves, so by default it uses the model solve ratio average, the default solve logic in Flag3D. But you've got the option to override it. So on your project, there is properties called solve strategy. So as I mentioned, the default one is the average unbalanced force ratio that Flag3D uses, but you can choose any one of the other defined in the Flag3D manual. You can use the maximum unbalanced force ratio or local, and then there's there's a special one actually that I've developed. What I've found is sometimes if you've got a free surface or a model with an open pit, and you have a lot of plasticity close to the free surface, you get that the model is very close to equilibrium, but it just doesn't want to get there, and we sit there for thousands of cycles to reach equilibrium. So what I've done is I've introduced a new fish function where you can specify that I want, if, for example, 99.9% of all my grid points are below a certain threshold, then the model is considered to be in equilibrium. So this allows that small area in the model that does not want to reach equilibrium. It basically not ignores it, but you can say that if the majority of my model is in equilibrium, it's considered to be in equilibrium. And you can obviously modify this percentage. So I'll just show you. If I select that option, and I build my solve data file, so called solve 5, this adds an additional fish function that looks like this. Fish define check conversion. So and then it's got this fish callback, check conversions every 100 intervals. So every 100 cycles, this function is called. It loops through all the grid points and determines what percentage of the total model grid points are in equilibrium. And if the percentage is greater than that 99.9 that I specified, the model is considered to be in equilibrium. So yeah, this is a handy trick for those of you that sit with the same problem as I often find. The model just don't want to reach equilibrium. This actually helps quite a lot. I think I'm actually finally ready to start solving the model. So you can do that simply from within IMAT, press the run button and start solving the model. Or what I like to do is I like to open up Flag3D, load the data file and run this from within Flag3D. So I'll just show you on disk what it looks like. So I've got my IMAT project. There's mine a.imat. And all that an IMAT project is just a folder with plain text information in there. So in the root level of the folder, there's each one of our plugins that's defined. So there's Geometries, there's the Movie Makers, Mesh Builder, there's our Flag3D plugin, for example. And in the Geometries folder, let's say, for example, in tunnels, you can see I've imported tunnels as STL files, or if they were DXF files, it's all there for you to go and grab and modify externally if you like. But what I want to do now is I want to go to my project one, look at my data files. There's a data files folder available to you. Here's all this data file, solve data files that created. You can simply go and open this with Flat 2D, run this, modify this, or go crazy, do whatever you like, and even do more advanced things. While we're on this, you'll see inside my project 1.flat3d project, there's my 10 or 21 mining steps that I've defined. Inside each of those, there's geometries that I've defined. And if once it's solved, there will be these stress.bin, displacement.bin, and plastic strain.bin files written out in there. There's also a grid.flat3d grid file that you can use anywhere else you like. And there's a joints.bin file, as I mentioned, for the ubiquitous joints file. So everything is plain text for you inside IMAT project to go and modify as you like. I am actually at the point where I can start solving this project, and I'm going to solve it overnight. And for tomorrow's session, we will post-process this and create some movies